So let's take a look at the last piece of the ISA, which is the memory map. As you saw, there are different kinds of memory. There's the RAM, there is the ROM or the flash, and there could be multiple ROMs on a system. And so as a convenience, we want to refer to all of them as if they were part of a single table. That is, we want to refer to them by their locations. So what we do is we refer to memory on the ARM ISA by a 32-bit address. So the addresses start from, again I'm using the convenient shortcut, which is 0000 with 8 zeros. That's the lowest memory location, and the farthest or the highest memory location is FFF. Now the total memory we can refer to is sometimes called the address space. The address space constitutes the number of locations we can refer to. With 32-bit address, we can refer from 0, 0, 0, 0, 8 zeros all the way up to 8 Fs. Each location is going to hold 8 bits of information. So we say that each location holds 8 bits of information. So memory location 0, 0 holds 8 bits of information, and every location holds 8 bits of information, which is 1 byte. Now let's take a look at the various banks within the memory. So the memory itself is composed of a region of memory which starts from 0 all the way up to a location which is 0x0003FFFF, which makes up 256K of flash or ROM. This is where we're going to write our code. So this is the part where we're going to put our code, constants, and stuff like that. Code, which is our instructions, and constants. Now we have our next bank of memory, which is going to be our RAM. This is a 32K of RAM on the board that we are using, which starts at memory location 0x2000 all the way up to 0x20007FFF. This is the RAM where we will store our data or variables, and again this is the volatile part, and also our stack is going to be part of this region. And now we have our all-important part of the memory map, which is the I/O. Now you may be wondering why we are looking at the memory and talking about I/O. Well, it's important to understand that the way we refer to I/O devices, again this I/O starts at 4000 and goes all the way up to 400FFFF, but we refer to I/O using a technique called memory mapped I/O. So the idea of memory mapped I/O is when we want to refer to a device, we simply read or write a particular location in memory, and that particular location in turn, for example, if I were manipulating a particular port, I would go to this location in memory, and a particular bit here might refer to an IO pin, and manipulating this bit is the equivalent of manipulating this IO pin. So this is what memory mapped IO gives us. Now there is some other IO. Some of these locations have other information, not all of them refer to pins. So in general, then these locations will refer to device registers. And there's more IO, and there is more IO, which is the internal IO, which, as opposed to the external ones that have something to do with external registers, external devices of some kind. This starts from 0xE000 all the way and goes all the way up to E004FFF. So what we notice in the memory map is that we have a lot of there are several sections of the memory, and we have 256K of RAM, 32K of RAM, IO ports, internal IO, and if you notice that there are chunks of space in between that I have not referred to. Well, these chunks of space in between are unused in that they don't have any we don't have any way of accessing them, and making accesses to these locations are considered errors. Now, what is also the case is that this picture obviously is not to scale. Notice that the 32K RAM that we have here and the 256K RAM leave out whole chunks of empty space in between. And so as a convenience, I'm showing this as if they were all contiguous and they are of a certain size, but in reality there is a lot of empty space that we are referring to. So now in this module we looked at a lot of important fundamental concepts. These were concepts that we expect you to understand and remember as you go forward. Because we looked at number systems that allow you to represent things. We looked at the guts of an embedded system, what's a microcontroller, and what is the ISA of a processor. We looked at the memory, we looked at registers. Now all this will only make sense if we do something with it. So what we're going to do from this point onwards is get our hands dirty and have fun.